So we're going to continue our session. So the next one is the vertical carbon fluxes. I think it's also a very important, probably large, very large carbon flux, but we didn't get quite a good handle on it. But I think the three talks here will enlighten what the field is going. It's heavily involved in CO2 fluxes. We didn't find much of the methane fluxes. Our first speaker is Kevin Kroeger from USGS.
Okay, thanks, Alec. So I'm going to talk about tidally restricted coastal wetlands. So we've talked a lot about trying to get at what a typical wetland outlet functions in terms of carbon budgets and cycling. Here I'm going to talk about highly managed wetlands. And what we found is that it's likely that in many cases there'll be hotspots for carbon dioxide and methane emissions. And since they're managed, there's significant potential opportunity for reductions of methane and CO2 emissions by restoring these wetlands. Okay, so since it's a lightning talk, I'm just going to give some bottom line kind of provocative conclusions. And this is intended for communicating with scientists, but also with the public. And the basic idea is, some of the conclusions are that for several centuries it's been widespread practice to both impound and drain coastal wetlands globally. And those altered wetlands produce substantial methane and CO2 emissions in some cases. And we're estimating that those emissions on the east coast of the United States alone are equivalent to millions of automobile emissions in terms of warming potential. And at present, there are no incentives to reduce those emissions, and so the situation is analogous to setting many thousands of forest fires around the world and just letting them burn for centuries, and then ignoring them in our attempts to reduce greenhouse gas emissions. And on the other hand, if we inventory the emissions and credit the reductions in those emissions, we can incentivize a new form of blue carbon. And so what we're talking about here is some conceptual models here. Here we have on the left a kind of typical healthy unaltered salt marsh, has tidal exchange. We have typically, except for in Iris's sites that we just talked about, often you have net uptake of CO2, you have increasing carbon storage, and that produces accretion in response to sea level rise. So they tend to be a carbon sink. And they have low methane emissions because the sulfate, abundant sulfate in seawater tends to inhibit methanogenesis. When we cut off the tide, two things can happen. People can take steps to intentionally drain a salt marsh. They want to use it for various purposes. And it's pretty well known that what that does is expose stored soil carbon that was previously inundated to oxygen in air. And you get a high rate of respiration of that carbon stock. And so you tend to be losing elevation and losing soil carbon over time. This is pretty well known, and in the IPCC wetland supplement, there is guidance on these emissions. But the other possibility is that the salt marsh might be impounded, and if you're in a relatively wet climate, usually you impound fresh water on what used to be a salt marsh. It may not be obviously an impoundment, it might not be open water, you might have a mixture of open water areas and just higher water table within your wetland. And then it transitions into a freshwater wetland or a low salinity wetland. And since fresher wetlands have lower sulfate supply, they tend to produce more methane. And so that in both of these cases, when we alter the wetlands, we're taking what was a system that had a cooling effect on climate and converting it into a system that has a warming effect. And so we wanted to know on a per unit area basis, were these emissions significant? And then we wanted to know what is the area of these types of settings. And so in terms of per unit area, we did some radiative forcing modeling, which involves tracking the pool of gases in the atmosphere from your particular ecosystem per hectare and calculating its impact on global temperature. And so here we have radiative forcing, 20-year cumulative radiative forcing on the y-axis. And these are positive values here indicating warming, and then we have negative values down here indicating cooling. And you can see that these coastal marine vegetated systems tend to produce pretty strong cooling, on par with or stronger than terrestrial forests. And if we drain those marshes, depending on some circumstances, or if we impound them, we take those cooling systems and we convert them into very strong warming systems. And we have 20-year emissions from an automobile here for comparison to 1 hectare warming. And so then the next question is, what's the surface area of this type of setting? And it's, the geography is difficult to quantify. They're spatially extensive. A lot of these systems are small. They're generally not mapped. And in often cases, they're no longer recognized as a former salt marsh. But they are ubiquitous across the coasts. And here we have 3 examples. This is the Herring River system, which is in the Cape Cod National Seashore on the Outer Cape. And that's 400 hectares of former salt marsh that's tidally restricted here with a dike. And there's an effort to restore tidal flow here. And we're trying to quantify the greenhouse gas emissions and the carbon stocks here, the changes that are predicted with restoration. This may be credited in a carbon market ultimately. Or we may have very small systems. This is right here in Woods Hole, and this is former salt marsh that was blocked off by a railroad that's now a bike path. And that would be predicted to be a pretty strong methane source because it's a much lower salinity. And then here we have Prime Hook National Wildlife Refuge in Delaware. This is a large system. It's about over 4,000 hectares altogether, but 1,600 hectares of it were inadvertently restored when Hurricane Sandy opened the dike there. So that went from a freshwater impoundment to a salt marsh. And so we pulled together the data that we could find where it's mapped. There's some mapping that's been done of tidal restrictions in New England. There's some published data, older published data on dike and impounded wetlands in the southeast for waterfowl or mosquito management. And on the whole, we estimate that about 27% of tidal wetlands on the east coast of the U.S. are affected in this way. And the emissions, that equates to about 2,700 square kilometers with 28,000 to 145,000 tons of enhanced methane emissions. And so this provides a significant opportunity to reduce emissions if we can inventory these emissions in the U.S. greenhouse gas inventory, and there's an effort underway to do that. And that's